Hi everyone, I want to add one more pair of shortcuts. It's really just one shortcut, but there's a special case that's really nice. So we'll give it as two shortcuts for now. And then we'll get into practicing using some of these things. So exponential functions are really nice to pair with power functions, partly because a lot of times people confuse them. So note that an exponential function has the variable in the exponent, whereas a power function is like x cubed, the variable is in the base. It's really important that you distinguish between those because their shortcuts are very different. Okay, so let's get started as usual. If we want to find the derivative of e to the x, we're going to take the limit as h goes to 0 of e to the x plus h minus e to the x all over h. And we can get a little ways with this algebraically, but we are going to get stuck and we're going to have to do a little bit of magic. Okay, so what we can do algebraically is we can split up the e to the x plus h. Exponent rules say that's exactly the same as e to the x times e to the h. Remember, the rule says if you're multiplying two things with the same base, you would add their exponents. We're using that in reverse. And that does allow me to factor out an e to the x. So we'll have limit h approaches 0 of e to the x times e to the h minus 1 over h. And I can even do better than that. I could split that e to the x out of the fraction really easily. As long as we're multiplying, it doesn't matter if you move that out in front of the fraction once you've factored it out. But what's really important to me is to notice that this is e to the x, and we're taking the limit as h goes to 0. As h goes to 0, nothing happens to the e to the x part. Absolutely, the e to the h is changing and the h is changing, but the e to the x, now that we factored it out, we can actually put it totally outside of the limit. So we're really looking at what is the limit as h approaches 0 of e to the h minus 1 over h. And this is where we have to just kind of be a little bit tricky. So I'm going to jump over to Desmos so that you can see what we're getting out of this limit. And then we'll look at the a to the x as well. So I've already typed this in, and I love this in Desmos. This wasn't initially true, but Desmos now understands function notation. So I have just called this f of h, and that makes it really easy to just plug in. We're letting h go to 0, so I plugged in things that are very small negative numbers and then very small positive numbers. And I think it's probably believable here that our limit is actually approaching 1. You can also see it in the graph as you come down here, same sort of thing happening, getting really close to 1, and then right at 0, it's undefined. I'm jumping over 0, but you hopefully believe me. Okay, so let's go back in here and see what that means. If this whole thing goes to 1, what we find is that the derivative of e to the x is e to the x. And this is kind of magical. This means when you're looking at a graph of e to the x, the y value is always the same as the slope of your tangent line. So wherever you are on that graph, it doesn't matter where you are, whatever your y value is, that's equal to the slope of your tangent line. So like easiest shortcut ever to remember, the derivative of e to the x is e to the x. Add that to your list. And I want to do kind of the same thing for a to the x. This one's a little less obvious, but the algebra all works out the same. So hopefully you can kind of see how that's going to work exactly the same. And we end up here. The limit as h goes to 0 of a to the h minus 1 over h. So I want to go in and just play around for a couple of values and show you what you get. Someone had to figure this out for us. It's not something that I think we immediately would have guessed on our own, but thank goodness they did that. So I'm just going to jump in here and let's just try a couple of these. So first is 2. So this would be if we're trying to take the derivative of 2 to the x, we'd end up with this 2 to the h minus 1 over h. And you can see our values here are really right around 0.693, somewhere in the ballpark of that. But that doesn't jump out as anything special to me. And what I'm hoping to see is a pattern here. So I'm just going to let you in on the secret. It turns out that that magic number that we're getting from the limit is the natural log of 2. So this is what we're approaching, is this natural log of 2, 6.93147. And as we play with this base, so there's what we're getting if we do, so this would be working on the derivative of 6 to the x. We get about 1.79. And if you'll notice here, that happens to be the natural log of 6. So not very proofy here, but it turns out that the magic thing that we get from this limit when it's not base e is the special one, is the natural log of a. So it turns out that the derivative of a to the x is a to the x times the natural log of a. And I mentioned earlier that it's really just one shortcut. So just to point it out here, you can memorize these separately, but what's going on here is that if a happens to equal this magical Euler's number e, about 2.7, then we get e to the x times the natural log of e. And remember that the natural log of e is always 1. So the shortcuts actually agree. This one is also telling me that the derivative of e to the x is e to the x. You just have to remember the fact that the natural log of e will be 1. And that's why we don't see that natural log floating around. Okay, so if you have a power function, x to a number, you're going to drop the power down, and the new power is 1 less than the old power. If you have an exponential function where your variable is up here in the exponent, the derivative of the exponential function is exactly the same function with potentially this extra constant that pops out, natural log of a. And that is a constant. That's not an x getting plugged into the natural log, just a number. So we're just popping out a constant multiple that does involve a natural log every time we take the derivative of an exponential. So hopefully that's somewhat convincing. Next we'll jump in and we'll start practicing.